Okay, the conclusion. Getting that inverse. The properties we're going to use. First one, the points get turned around. So if I have 2, 0 on one graph, I have 0, 2 on the inverse. And if I have 4, 2 on one graph, I have 2, 4 on the other one. So I have to have those points. Then the next one, the next rule that we're going to use, the graph has to reflect across the line y equals x. And so there's the line y equals x. And so we're going to have to kind of use our imagination a little bit. And anything that you were to draw me that looks like you tried would be okay. I just moved that because it's going to be in the way a little bit. So we now envision a line that looks as if I took my paper and folded it across that line y equals x, the two graphs would lie on top of each other. And the best to my abilities to draw it might look something like that. And so there's the graph of f inverse. That we try to make it, we can flop, we can turn the points around, and then the graph itself should look like we've reflected across the line y equals x. Let's do it again. So this point here is -1, 0, and this point here appears to be 1, 2. So that means we're going to have 0, -1, right there. And we're going to have 2, 1. I'm going to have to move this, it's kind of in the way. I'll just move it up a little bit. Then we're going to have the point 2, 1. Right there. The points get turned around. Now, if you wanted, you could come up with more points. Those are the 2 points that I put on the graph, but notice we have a nice easy point here, 1, 0, and so that tells me that's supposed to be in green. That tells me that 0, 1 will have to be on the green graph. You can pick more points than what's shown there. And then doing my best to actually draw this thing. First of all, it's going to get reflected across the line y equals x. So there is my line y equals x. And then we try to do the best that we can to graph something that looks like it's going to be flipped across the line y equals x. And I'm not even really sure I can draw this. But I will do my best. So I think this is going to have to come out somewhat like this. And then like this and like that. And like that. That's not a great graph. It's not horrible. It's not that bad. But you make the effort. No one is expecting wonderful works of art here from you. And so there's something that looks like I at least tried to get it to be y equal, to reflect across the line y equals x. I've seen worse pictures. And like I said, if this was, you're watching this and you're one of my smaller classes, and I'm actually seeing your work as opposed to the huge classes where it's all multiple choice on the computer. If you're in one of my smaller classes and it looks like you tried, you're going to get it, especially when you show me that you know that the points get swapped around like that. Now, one trick you can do if you really want a better looking graph and you really care, you can take the given function and take your pencil, and really color it in. So it's nice and shiny and dark. Then you could literally fold your paper along y equal x, and then rub really hard to transfer the pencil onto the other one, and then you'd have a pretty good graph. But that's good enough. Doing it one more time, same thing. Let's pick a couple points here. So this point right here looks like it's 0, 4. And this point here looks like it's -2, 0. So that means on the graph, I'm going to have 0, -2, which looks like it's right there. And I'm going to have 4, 0, which is right there. Then the y equals x line is right about there. There's y equals x. And so then just do your best to draw a line that seems to reflect across that. So it would look something like that. And my graph is a little bit off here. The red line should be going through this point right here. So my graph is a little bit off. So we will fix that up with my whiteout. We can fix that up. There, that looks a little better. And there's the graph of my inverse. Okay, so that's the graphical property of inverses. Then the last thing we're going to do, and we're going to work with this concept a couple times, we're going to find formulas for inverses. So finding formulas for inverses. And this really should say in simple cases. Basic cases. Because finding the formula for an inverse frequently is not really possible. When you go into trigonometry and you study functions sine and cosine, what you write down for sine x for its inverse is inverse sine. What you write down for the inverse of cosine x is cosine inverse. There isn't a formula. And so that's why I said it was so important to remember these properties, because there will be instances where you need to work with the inverse function, but you don't really have a formula. And so you take everything you know about the original function, use these properties to find out information about the inverse functions. But in simple cases, there is a way to find formulas for inverses. And it's just a little 4-step process here. 1, if necessary, rewrite as y equals. 2, interchange the x and the y. 3, solve for y. 4, replace the y with f inverse. So let's actually do it. Find an equation for f inverse. So doing my steps. 1, y equals 3x plus 6. 2, interchange the x and the y, and I literally mean just swap it around. 3, solve for y. So x equals 3y plus 6. Let's just move that 6 to the other side. So x minus 6 equals 3y. I'll go all the way up there. So that's 3y equals x minus 6. Divide both sides by 3. And I get y equals x minus 6 over 3. Or I can say f inverse equals x minus 6 over 3. The 3 and the 6 don't cancel. Remember, you only cancel in a fraction if you can cancel from all terms in the fraction. So there's my formula for the inverse. 2, verify the rule for f inverse by finding f of f inverse and f inverse of f. So f of f inverse. So like this. And so I start on the inside, replace f inverse with its formula, which was x minus 6 over 3. Then apply f's formula, but replace the x with what I have in parentheses. So I keep the 3. I get to the x. I do the replacement. And then the plus 6. And lickety-split, the 3's cancel. So I get x minus 6 plus 6, which is x, which is what I wanted to see. Doing the other way around. Start on the inside. Use f's formula. which is 3x plus 6. Then use F inverse's formula up here, replacing the x with 3x minus 6. So here's my formula. I start with x. I do the replacement instead. 3x plus 6. Then I keep the minus 6 and the 3. And I get 3x over 3. I get x. And because they're both x, they are inverses. So we know that our formula is right. Then graph both those. I'm just going to do them on a calculator real quick. You could graph them by hand, but calculator is fine here. So I'm just going to graph them on a calculator here. And so we had one of them was 3x plus 6, and the other was x minus 6 divided by 3. And notice the entire numerator is in parentheses. And I have no real reason why I put them in y2 and y3. That doesn't matter. Now I'm going to hit here, not zoom 6, but zoom 5, zoom square. For reasons I told you about before, that when we were talking about parallel and perpendicular, we said the standard window would distort things. The standard window would distort this here. And so there are my two functions. Then remember what we're hoping to see. So I'm going to add one more line here. I'm going to add in line y equal x. And then just to kind of make it look fancy, I'm going to arrow all the way back till it's on that diagonal line. You see it's flashing. And if I hit enter, it's now flashing with a thick line. And I think, hey, I don't know what it's doing now. And I kept hitting enter, and now it's flashing with dots. You can't really see it too well, but I just kept hitting enter till it flashes with dots. And now I'm going to graph it. And it's sort of dotted in there. You really can't see it very well. I should have gone with a thick line, but anyway, we'll zoom in a little bit. There's my graph, and you can sort of see that the line I added, y equal x, is now dotted. You wouldn't have to do that. But what we're looking for here is that reflection property, that the two original functions I put in there do look like they reflect across the line y equals x. Now that was on zoom square. Look what I get if I hit zoom 6, which we almost always do. There's that y equal x line. There are my two lines. And it actually doesn't look too bad. It still looks, okay, so everything I did there about the zoom 5, it actually doesn't look too bad. And so, yeah, zoom 6, zoom 5, I guess it doesn't matter there. I think the zoom 5, the zoom square window, looked a little better than this window, but not too bad. Okay, that's the graph. And like I said, just do it on the calculator. You can ignore everything I said about zoom 5 versus zoom 6. It turned out not to be that important. That's me being lazy and not wanting to do another video when there was nothing essentially wrong. Use interval notation to do the domain and range. Okay, f of x equals 3x plus 6, and f inverse of x, f inverse of x, which is x minus 6 over 3, which is the same thing as 1/3 times x minus 6, which is the same thing as 1/3 x minus 2. The reason I did both of those is they're both polynomials. So we learned earlier that the domain is negative infinity to infinity. So that was a little fact that we had earlier, that the domain of polynomials, remember polynomials, whole number, exponents, no variables and radicals and denominators, we learned that the domain of polynomials was negative infinity to infinity. So the domain of both f and f inverse is negative infinity to infinity. Now this asks for both the domain and range. So cliffhanger, on the next video, we'll figure out what the range is.